Now, before we start learning objectives 7, 2A, B, and C, I want to talk about the sampling distribution of P and show you an investigation that we actually did in the classroom that is worth the time to look at. The question here was, what would happen if we took many samples and recorded P hat if I had a jar of pennies? So what I did is I have this very large jar of pennies with different dates on it, and I had students come in and take a sample size of 5 from this large collection of pennies. They then calculated what was their P hat was the proportion of pennies in the sample that were minted in the 2000 year period. So of their 5 pennies, if they had 2 of those, they would do 2 out of 5 or 40%. Now I will tell you, this container of pennies, I had 500 pennies, and of those, 156 actually had a year of 2000 or higher. So about 31.2% is the true population proportion for that jar of pennies. Okay, so I had each student record their values on a class dot plot, and we used various increments. So we did that first with size 5, okay? Then I came back and said, all right, folks, let's do it now. What if the sample size isn't 5, but what if it's 10? And we're trying to see if the sample size is going to make a difference on how accurate we can get to the true population proportion. So in this simulation, again, what we did, this was a sample size of 5, and we did it 16 times. Now, the mean of all of our P hats ended up being 25%. Well, here's what all the P hats look like. We did the distribution. So our sampling distribution of the 16 outcomes, I added up all of these proportions and divided by 16. The mean of these is about 0.25. So our mean is coming in right about here for the scenario. Keeping in mind the true population proportion was 31.2%. So then what happened if I had the students go back and say, change your sample size to 10? Or what if I had them double it and change it to 20? How would the sampling distribution change? And what would the mean of all the little proportions look like? So this is a new notation. It is the mean of the P hats is how you say this. So the mean of all of our P hats in a sampling distribution of proportions is this calculation. Now, I actually didn't have the class continue on and do a sample size of 10 and 20 because it does take a long time. So I showed them the results of a computer simulation that the author of our book actually did. So let's take a look at that. Now here, they had a jar of all of their pennies, and it was a little bit different in terms of their true population proportion. Ours was 31.2%. They actually had 29.3% of their pennies were minted in the 2000s or higher. So what they did is now they went and ran an SRS of 500 unique samples. Remember, we only did 16, so 500 is better. But they did an SRS of sample size 5, 10, and then 20. And they graphed that. So what you're seeing here is a sampling distribution of the proportion of pennies that were 2000 or higher for all of those samples of size 5. Here's size 10 and here's size 20. We've talked about this a lot, variability. Clearly, there's less spread as you get a larger sample size. So the conclusion that we can actually make about this is, notice we're trying to get the true population parameter of almost 30%. So the 30% on here is about right there. Right here's our 30% here, and then our 30% is right there. Which one of these is more close to the true population proportion? Clearly, it's the sample size 20. So it says here, notice all 3 distributions have the mean of about 0.298. So if I add these up and take the average, it's going to be close to it. So it's fairly an unbiased estimator, no matter on the sample size we're choosing. The value of the true proportion of minted pennies in this population, again, was 0.293. The spread, however, gets smaller as the sample size increases, and the shape actually becomes more symmetric and less skewed as the sample size increases. So yes, we love that the variability gets under control, but even more so, we really like that the shape of the sampling distribution becomes more symmetric. It's almost approximately normal. The nice thing about getting towards an approximately normal distribution is it's going to allow us to use the normal CDF and calculate approximately normal probabilities, which is the point of what we're going to lead up to when we hit chapters 8 through 12. Okay, I'm going to switch gears on that penny example. Again, this time they want to estimate the proportion of pennies minted before 1976. So this is a different type of statistic. Is it going to matter? So they're using the same population. Their true proportion, by the way, in their jar of pennies was 9.2% are before 1976. Again, they did another SRS of 500 trials, sample size 5, 10, and 20. And you're going to see the results right here of what we're seeing. Here it says, notice that the means of the distribution are about the same. Again, we're shooting for about almost 10%. So if you look at that, we're going to be somewhere in there, somewhere in here, and somewhere in here for the true population proportion of 9.2%. So they're going to say here, also notice the spread of the distribution gets smaller as the sample size increases. Not a real surprise to us, right? And the shape of the distribution becomes, again, more symmetric and less skewed in this case, again, as that sample size increases. Although the shape is clearly right skewed when n is equal to 20 in this case. So it's more of a right skewed shape, fine. But here's the conclusion. For all three samples, the distributions were more skewed when the proportion is 9.2% than when the proportion was 29.3%. So what we're seeing here is, in general, is the closer that the true population proportion is to 0 or 1, the actually more skewed the distribution of our p-hats will be for the sample size that we're given. So again, this second example, our true population proportion is closer to the number 0 versus our 29%, which it's not. And we're going to get more of a skewed distribution, and that is how it works. So now let's formally talk about 7.2a, b, and c. In A, we're going to find the mean and standard deviation of a sampling distribution of a sample proportion based on a various sample size. In B, we're going to check whether the 10% and the normal condition are being met. And in part C, we're going to start to use the normal approximation to calculate probabilities, because remember that sampling distribution is actually becoming approximately normal, which allows us to do probabilities then. If you remember back in chapter 1, you had to distinguish between a quantitative and a categorical variable. And this is why. You're going to have to start realizing what type of information we're looking at. When we do sampling proportions, sample proportions arise most often when we're interested in categorical variables. Why do you compute a proportion? Well, if you ask a question something like this, what proportion of the U.S. had watched a certain TV show? The answer is a word. Well, you can't compute the mean of a word, but you can compute the proportion of people that said, yes, I watch it, or no, I don't watch it. So before you start any problem going forward, you need to start thinking about, is it categorical or quantitative? If it's categorical, we're going to look at proportions. And we're going to get to it soon here, but if it's quantitative, we actually look at the means. So when we're taking a sampling distribution of a sample proportion, you're going to be asked to find the mean and standard deviation, because ultimately we want to do a normal CDF probability, but remember we need a mean and standard deviation. So what they refer to it now in a sampling distribution is the mu of p hat. This is the mean of all of the p hats. Remember the distribution or the dot plot of all of those proportions? Add them up and take the mean. So how do you find the mean of all your p hats? We assume the mean of all the p hats is the true population proportion. Okay, how do you find the standard deviation? The standard deviation of all the little p hats of all of our samples is equal to the square root of p times 1 minus p over the sample size that was used. Now, these two formulas are found on the AP formula sheet. Now, in order for us to be able to calculate this mean of the p hats and this standard deviation of the p hats, we have to make sure some conditions were met. So there's 3 conditions. The first one is we have to make sure that it's a random sample. And a lot of the times you're going to be able to see this just in the problem. They're going to say they took a random sample. So you're going to say, yes, it's a random sample because you talk about it in context for the problem. Now, for the independence rule, you have to check the 10% condition. And to prove independence, you show the 10% rule follows, and if it does, that allows you to actually compute the standard deviation. So remember the 10% rule, what we said is n is our sample size, capital N is the population. Is our population greater than or equal to 10 times the sample size? If it is, the independence rule is met. Now, very importantly, the normal condition must be met. Is the distribution going to be approximately normal? To check that for proportions, all you do is you have to show this calculation. Is the sample size times the population parameter for the proportion greater than or equal to 10? And is the sample size times, really, this is the probability of failure, 1 minus p greater than or equal to 10? Because remember what we saw in our analyses and our simulations, that as that sample size increased, the distribution actually became more approximately normal. So we have to do and check the size for this case. This here allows us to actually do the normal CDF calculation. So let's go ahead and actually compute a probability question. First year college student. A polling organization asked an SRS of 1,500 first year college students whether they applied for admission to any other college. In fact, 35% of all first-year college students applied to colleges besides the one they're attending. What is the probability that a random sample of 1,500 students will give a result within 2 percentage points of this true value? Now, keep in mind here, the 35% is what their actual sample gave them as their p-hat. So what is it that I want to find? I'm going to state the problem. I'm going to make it short and sweet. Here's what I want to do. What is the probability that the p-hat is somewhere within 2 percentage points? So too low and too high. So between 0.33 and between 0.37. I can compute this probability using normal CDF if I check the conditions and prove or show it's approximately normal. So you must show random, independence, and normalcy. Going forward from here on to the rest of the book, you must show the conditions. This is very important. First one's very easy. Is it random? Yeah. You told me you took a random sample of 1,500 students. That's all you have to say. Let's check for independence. The independence test is the 10% condition. So remember, for independence, I'm going to show the population is greater than or equal to 10 times the sample size. In this case, the population here, when we put this in, 1,500 into here is going to say 15,000. Is n greater than or equal to 15,000? Sure. I'm going to say here, clearly there are more than 15,000 first-year college students. A lot of the times, I will tell you in this independence condition, they're not going to tell you in the problem how many are true college students are in the population. They just want you to use your gut test and say, well, yeah, there's more than 15,000 students going to college. It's met. Now, this again allows us to compute a new mean and standard deviation. So, what is the normalcy? Is it met? The normalcy condition says that we have to test n times p and n times 1 minus p. Both of these have to be greater than 10. And you have to actually show that you're doing this calculation. This right here means the normal condition is met. And what I can say is that this is going to be approximately normal. Now, the other thing I need to highlight, notice I didn't say it's normal. I said it's approximately normal. This is incredibly important. You kind of want to be wishy-washy here. If you said when you check this condition that it's normal, that is not true. It is not exactly normal. You must kind of cover your butt and say the word approximately normal. Okay, now we have enough information to actually do our probability question. We do these just like we did in Chapter 2, folks. They're not anything different. The only difference is I do have to compute the new mean and standard deviation. So in this case, the mean of the population proportion is the same as what we're assuming, so it's 35%. The sample standard deviation of the population proportions, I'm going to use the formula, which said p times 1 minus p over n. Take the square root, here's our answer. Okay. State our parameters. Well, the parameter is that we think the true population proportion is 0.35. Okay. And now let's go ahead and actually look at the graph. So if I were to make a graph, I'm going to do a quick little sketch. The true proportion, that's going to be our mean of our p hats, is somewhere in there. It's approximately normal. And we want to look at the probability between 0.33 and 0.37. So we want this shaded region. All I have to do at this point, I'm going to use my calculator. I'm going to compute a normal CDF of my lower bound, my upper bound, the new mean, and standard deviation. Now, for calculator speak, I've got the mean and standard deviation stated. I said it's normally distributed. I'm done. That's all I have to show. The answer for this is about 89.61%. Now, I think part C is a good review question, maybe for a possible multiple choice. Find the z-score. We could do that. That's not hard. The z-score, remember, is just going to be our calculations in this case. How do we convert 0.33? And how do we convert 0.37? Well, the 0.37 is our estimate minus the mean over standard deviation. Same for 0.33. Now, could you go ahead and compute the probability for this using z-scores? Sure. How would you make the adjustment? Well, what I would do, I would use my lower bound would be negative 1.63. My upper bound would be 1.63. My mean in this case would be 0, and my standard deviation would be 1 because the data has been standardized. All right, now if we wrap this up, find the probability and write the linkage statement it says here. Again, here's exactly what I just talked about if you wanted to do the normal CDF using the z-scores. Honestly, if they don't ask for it, I'm not even going to do this lower half of it. I'm just going to stick with what I did in parts A and B up here and call the problem done. Number 4 is a good review. Discuss the probability in the context. Make your conclusion. Fine. We said the answer was 89.6%. So what I'm going to say is about 89.6% of all SRSs of size 1,500 will give a sample proportion within 2 percentage points of the true proportion of first-year college students who applied to other four-year colleges. It's incredibly wordy, but that is the context of our true population that we're looking at. Now, this last question is worth really paying attention to. It says here, standard deviation. What sample size would be required to reduce our standard deviation of the sampling distribution to half of the value that we found in the question? Then they're going to say, what about a third? Well, let's remember the formula for standard deviation. It's this right here. Now, what we found the original standard deviation was, it originally, p hat, was 0.0123. Well, they want to find half of that. So let's take half of that number and put it here. Okay, I can do that. Half of that is going to be 0.00616. I'm going to use the same information that we did. This was p, this is 1 minus p, and this is n. They want to know what should the sample size be to have less variability. Well, our sample size here was 1,500. I want to be half as variable. So what should it be? Let's solve it. Now, to solve this, a good way to go through it, if you're not strong in your algebra, I personally would square both sides. That's going to eliminate the square root. Then what you could do once that is done is you can kind of cross multiply if you want. The n would then go up, and this value here would come down. When you do that, what you're going to see is, again, I moved the n up and I brought this down. Remember, this number here was being squared. Technically, this little square root symbol should not be there, so ignore that. What we should have is, because we've removed the square root here, is 0.35 times 0.65, and we divide it by 0.00616 squared. To reduce our variability, we're almost going to have a sample size of about 6,000. So we're almost doing it really 4 more times larger. You could do this problem for the 1/3 component. On the 1/3, let's just take this value, cut it, divide it by 3, and put that value here and repeat the problem.